Hello, friends. Welcome back to Material Science and Metallurgy course. Myself, Dr. Varun, and I'll be teaching about some of the important concepts in the material science and metallurgy. So let us continue and try to understand. In this unit, we will be discussing about what is called as the triple T diagram. But before we go into the video, let me again tell you that previously we have discussed about iron carbide phase diagram, which is very important. And if you have not watched that video, please go watch that video and come back, because if you need more clarity on this video, please first watch the video, and only then you can continue watching this triple T diagram. It all makes sense then. So let us understand the journey of austenite with a small experiment like shown in this particular slide. So we know that austenite is not stable below 723 degrees centigrade, and it is going to transform to pearlite. So austenite is going to transform to pearlite only at 0.8% of carbon. That is also known to us. But what if we have certain delay? That means what happens if austenite is made to transform at different time intervals. So let us take at different subcritical temperatures and then understand. That means 723 we know. What about at lower than that? So let us take a separate experiment wherein we hang. So you can see in this one, we have 6 such specimens hanged using a small thread in a bath. Now this bath is held at different subcritical temperature at below 723. So let us take the first specimen, hold it at that subcritical temperature, let's say 723, so 623. So at that 623, and hold it only for 30 seconds and immediately dip it in the cold water in order to understand, in order to arrest it and see how it transforms. Since you are not giving sufficient time to transform, this 100% austenite will remain 100% martensite. So when all the austenite, that is gamma iron, is arrested and we freeze it then and there itself, it forms what is called as martensite structure. So let us take the other specimen, that is this one. So there we hold it for 6 hours before cooling it. So at that subcritical, I said 623 degrees centigrade, which is below 723. So you are holding for 6 hours. So since it is 6 hours, it is transformed 5% to pearlite. Only 95% is austenite, and already there is a 5% of conversion to pearlite. So when this is brought to cold water, this 95% of austenite, which is still remaining as austenite, only will convert into martensite. And 5% pearlite, which is already formed, will remain 5% pearlite. Similarly, at 18 hours, it will be 75% austenite, 25% pearlite. So 75% martensite will be converted, and 5%, 25% pearlite will remain same. And after, let's say, 21 hours, it is 50 percent austenite, 50% pearlite, so 15% martensite and 50% pearlite. And finally, at 66 hours, you can see complete pearlite has formed. Now, after forming complete pearlite, it will remain complete 100% pearlite, even if you cool it to room temperature. So this experiment is at one subcritical temperature. Let us imagine that you perform this at several subcritical temperatures at different time intervals and plot it on, superimpose them all on a single curve, single graph. That is nothing but this time temperature transformation or isothermal transformation. So basically, in the previous slide, what you have seen is, if, let's say, 0% austenite, and then you have 50% austenite, and then 0%, 100% conversion. So when we plot at that subcritical temperature, you may get the beginning of transformation, 50% transformation, and ending of transformation. When you superimpose all such subcritical temperatures, let's say 623, 523, 423, and time intervals at different levels, you'll get this beginning of transformation, 50%, and ending of transformation. What it indicates is Nothing but this is a triple T isothermal curve, or it is also called as S curve or a Bain curve. So basically, if you see, you have a nose region. So this is the nose region, and above the nose region, you have pearlite, like coarse pearlite, medium pearlite, fine pearlite, upper feathery bainite. Below the nose region, you have upper feathery bainite, and lower or acircular bainite. And if you avoid these transformations, you start martensite. So martensite to start 50, 90, and 100% martensite. So the RC, that is Rockwell hardness, if you see, perlite has got 15, medium perlite has got 30, fine perlite 40, upper feathery bainite has got 40, and then lower acircular bainite has 60, and martensite has got 64. So the hardness has increased tremendously. And this is the microstructure you can see here. Now, let us understand, why do we use it? Where do we use this transformation? So let's say austenite, and then austenite, we know it is not stable below 723. So if it is cooled very slowly, then you'll end up getting perlite, which is coarse perlite, and then you have fine perlite, or bainite, upper bainite, lower bainite. And this is how, with the decrease in temperature and transformation occurs, and this is called as isothermal transformation, time dependent, basically time dependent transformation. But this is not the true one, because you are trying to cool the uh, structure and then try to get the different transformations, which is very difficult. But what if I get coarse perlite, fine perlite, martensite, and perlite, with the rate at which it is cooled? That is, the if you control the cooling rate with the increasing cooling rate, then this is possible in industry. So this is called as continuous cooling transformation, or CCT. So you have two things here. One is time temperature transformation, triple T. Another one is continuous cooling transformations, CCT. What is the basic difference? Let us quickly understand. So let us have an x-axis time, which is in log, and then you have temperature. And we have a 723 degrees centigrade, which is austenite. Above this, you have stable austenite. Below this, you don't have a stable austenite. So previous experiment will give us this beginning of transformation 50% and end of transformation. So this is how you got the plot. So once we got the plot, you have a nose region where it is somewhere 550 degrees centigrade, above which you have perlite, below which you have a bainite. So austenite is stable, unstable here, right? And you have, let's say, starting with coarse perlite, perlite, fine perlite, upper bainite, acircular or lower bainite, and below this you have martensite, right? And we also have seen with this the increasing Rockwell hardness as well. Now, for example, if at all I want uh, perlite, and I am using temperature as a medium to cool it. So if I at all perlite is needed, I need to form temperature from austenite, quickly cool to perlite, and then quickly brought it to room temperature. So this is little complex when it comes to cooling it at a rapid rate. When I want perlite, fine perlite, this is how you need to travel. Similar is the case with upper bainite and bainite. And this is how you get martensite. So suppose if at all I want martensite, you can imagine from austenite, it has to rapidly cool to martensite. All these are practically difficult challenges that we have in getting the microstructures when it is in time dependent transformations. So when I say a different rate at which it is cooled, you are able to get the uh, medium controlled by using air as a medium, oil as a medium, and then we are trying to get the required cooling rate. And this is the difference between uh, time temperature transformation and continuous cooling transformation. So this is also having a rate at which you can critically control exactly that is needed to form austenite to martensite, and touching the nose region tangentially. This is called as critical rate of cooling. That means the rate at which it is transformed is exactly sufficient to convert austenite to martensite. So this is called as critical rate of cooling. I hope you have understood the CCT triple T diagram in brief. So those who have not subscribed yet, please do subscribe and encourage for giving more such updates on materials and metallurgy courses. I hope you like the video. Please share it with those who are interested to learn more about material science and metallurgy. Thank you. Thank you for watching.